Hello, let's continue our Sudoku adventure with Pincer Move by Strosahl. So we have normal 6x6 Sudoku rules. That means in each row, each column, and each 2x3 box, we are placing the digits 1 to 6 exactly once each. We also have these little killers outside the grid. So they have a number and an arrow. What we do is we follow the arrow and we hit every single cell until we reach the end of the grid. So here it's these two. With this 11, it's all 6 of these. And the number is what the sum is. So these two sum to 6, these 6 sum to 11, these two sum to 9, etc. I guess the etc. is this 8 and this 7. Anyway, so that's how little killers work. They do not introduce any new non-repeat constraint. So I'm allowed to say put a 1 here and a 1 here and a 1 here and a 1 here, right? What I can't do is put another 1 here only because it's in the same box, right? Sudoku still says I can't repeat the 1. The little killer doesn't care, but the Sudoku does. All right. In addition to that, we have these blue lines in the grid. What you do is you segment the line based on where they cross these bold boundaries between boxes. So we could call this, say, the green segment, this the purple segment. This one, it's actually 4 segments because, every single time it's crossing a box. But anyway, on the same line, every segment has the same sum. So for example, let's say this was 5, 6 adding to 11. That would mean that these three, the 3 greens, also add to 11. Maybe we could do, I don't know, maybe like a 3, 2, 6. That also adds to 11. So this would be one way to fill this line, one of many. 11 isn't necessarily what it adds to. If this was 4, 6, maybe it would add to 10. Maybe we could do something like that. All right. But different segments on different lines do not have to have the same sum as each other. There's only segments on the same line that have the same sum. And that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. I mean, this 11 does jump out at me. We have 6 cells adding to 11. And that feels very low, but we don't base on feelings. We need to do logic. So how do we think about this sum? Well, we think about what we can think, since we think it's small, we can think about what the absolute minimum these 6 cells could add to. And so here, notice that we can split it up by boxes and say these two are in the same box. So they can't be 1, 1, right? They can't add to 2. The minimum they could add to is if they were a 1, 2 pair adding to 3. This can be a 1 on its own. This can be a 1, and this can be a 1. This can be a 1, 2 pair. So the absolute minimum would be 3 plus 3 is 6 plus 2 more is 8. Now 8 is less than 11, and that means we have what we call degrees of freedom. In this case, it's 3 degrees of freedom because we need 3 more to get from 8 to 11. So some of these, like this is not going to be the answer because some of these will have to increase such that we increase by 3. So that means that naively, and we're going to ignore this line for a second. Naively, what I can do is I can increase these 2s up to 3, right? I could do a 1, 5 pair. And if I did that, if we can just double check our math here, that would be 6, 7, 8, plus another 3 is 11. So our degrees of freedom is correct. So we can be anywhere up to 5 on these and on these. And then these 1s can be increased anywhere up to 4. Again, we're ignoring the line for a second. And so if this little killer were in a void, this is how I would pencil it. And I would say, well, in total, we're getting 3 higher than our minimum. Exactly 3 higher than our minimum, which could be a single cell increasing by 3 or multiple cells increasing by such that the total increase is 3. Anyway, now let's actually look at this line. This line is telling us that all of these are the same exact digit because the way we're segmenting this is into single cell segments. And so they all have to be the same. So that means that if I increase, like 1 is the minimum. If I increase the 1 to a 2, I'm not using 1 degree of freedom. I'm using 4 degrees of freedom. Well, not quite. Increasing from 1 to 2, this is still, if we look, the minimum could have been 2, 1, right? So these two don't increase, but all 2s would increase our degrees of freedom by 2, and all 3s would increase my degrees of freedom by 1 for these 2 and by 2 for these, and that would be 6. And so we can't be 3s. We're 1s or 2s, I suppose. Let's think about the 2s though. That would make, so all 2s would make this add to 8. So I would need 3 more between these two. And it's not actually possible to increase by 3 more. I can make them both 1. I can increase by 2, and that would make this add to 10. But I can't use 2s. And so how am I going to increase this by 1? I can't. Neither of these ones can increase to a 2. The next smallest I could do is like a 3 and a 1, which would add to 12. So we can't actually do all 2s, which means we're all 1s. Nice. Don't need them to be green. Now that they're all 1s, these add to 4. These add to 4. So I need 7 more. So these are either a 2-5 pair or a 3-4 pair. Okay. Can we finish the 1s? Yeah, this is a 1, and this is a 1. Okay. So now we know this 3-cell sum does not contain a 1. So its absolute minimum is 2, 3, 4. Actually, that's not even true. Because these two add to 9 based on the little killer. So if these add to 9, the minimum here would be 2. That's 11. The maximum here is 11. The max I can do is 5, 6. So if the minimum here is 11 and the maximum here is 11, we add to 11. So these add to 9 in some way, and this is a 2 to get us to 11. So that's not 2, so that's not 5. In fact, the 5, 6 pair told us the same thing. So how are we going to add to 9 without a 1 or a 2? Well, we never want 1 or 2. We're either 3, 6, which would be a 3 here and a 6 here, or a 4, 5 would be a 4 here and a 5 here. Okay. This is just 2, 3, 4 for the column. So these add to 8. So this is a 2 or a 3. We add to 10 or 11, which means we always need the 6, because we're either going to be 4, 6 or 5, 6. So these add to 8 without a 1. We never want a 1 anyway. So we're either 2, 5, not 2, 5. We're either 2, 6 or 3, 5. So we could do 2, 6, 2, 6 this way, or a 3, 5 pair. Now, if we were 3, 5, this would have to be a 2. And so we'd add to 10. So yeah, the 5 could go here because this would be 4, 6. All right. Unfortunate. I thought maybe there was this 5 wasn't possible or something, but it is. These two sum to 6 without a 1. So we're not 1, 5. So we have to be 2, 4. So this is the 4 and this is the 2. So this can't be 2, meaning this can't be 6. So this is a 3, 5 pair, making that a 2, making this a 4, 6 pair. No wonder it worked. And we're left with a 3, 5 pair here. So 3, 5. Okay, this one's not 2. What did these add to? These added to 7. So we have to be 3, 4. This is the 3. This is the 4. This has to be 3, 5. No, 3, 6 to add to 9. That's a 2. That's 5 and 3. All right. I think at this point it's just Sudoku. So this is a, oh, what's this one? A 5. This is 4 and 5. This is a 6. These two digits are a 3, 4. So this is the 4 and this is the 3. This finishes with a 6. These two digits are a 2, 5. All right. This digit is a 3. And these two, oh, we do have this 7. Okay, so that's 5. I wasn't done with all the little killers. That's 4 and 5. This is a 6. Down here we need a 4. That gives us 6 and 4. That's 5 and 6. That's 2 and 5. And these two are the 2 and the 3, and we're done. All right, nice puzzle. I enjoyed that, Strosahl. Yeah, this 11 was interesting because the degrees of freedom said these could be all 2s, but we couldn't actually make this add to 3, which was kind of an interesting extra check we had to do on all 2s. Cool. And in general, I liked the using the little killers to give us partial sums of these 3-cell sums, which was also neat. All right, cool. Well, let me know how you did, and if you enjoyed this, why don't leave a like, subscribe, and a kind comment below.